Today's LeetCode problem is 2402 meeting rooms 3. You are given an integer n, which represents the number of meeting rooms. These rooms are numbered from 0 to n-1. You are also given a two-dimensional array called meetings. Each meeting is represented as start time and end time, written as start I and end I. Each meeting happens during the half-closed interval from start I to end I, meaning the meeting includes the start time but does not include the end time. All start times are unique. Now, meetings are assigned to rooms using specific rules. First rule: each meeting should be assigned to an unused room with the lowest room number. Second rule: if no rooms are available at the meeting's start time, the meeting must be delayed until a room becomes free. When delayed, the meeting keeps the same duration as the original one. Third rule: when a room becomes free, the meeting with the earliest original start time gets priority. After all meetings are processed, your task is to return the room number that hosted the most meetings. If multiple rooms have the same maximum number of meetings, return the room with the smallest number. Remember, a half-closed interval means the meeting includes the start time but excludes the end time. That is the full problem statement. Let's understand this example one clearly by thinking in terms of how the system behaves over time. We have 2 meeting rooms, numbered 0 and 1, and 4 meetings with different start and end times. Meetings are always considered in increasing order of their start time, and whenever a meeting begins, we try to assign it to the lowest numbered room that is currently free. At time 0, both rooms are available, so the first meeting goes into room 0 and stays there until time 10. When the next meeting starts at time 1, room 0 is already occupied, but room 1 is free, so that meeting is assigned to room 1 and runs until time 5. Now when the meeting at time 2 tries to start, both rooms are already in use. Since there is no free room, the meeting is delayed rather than cancelled. The same thing happens with the meeting that starts at time 3. Both of these meetings wait until a room becomes available. At time 5, room 1 becomes free. At this moment, among all delayed meetings, the one that originally started earlier is given priority. That is the meeting that originally started at time 2, and it is scheduled in room 1 for the same duration, ending at time 10. Finally, at time 10, both rooms become free again. The remaining delayed meeting is then scheduled, and as per the rule, it goes to the lowest numbered available room, which is room 0. When we count how many meetings each room handled, both room 0 and room 1 end up hosting 2 meetings each. Since the problem asks us to return the room with the smallest number in case of a tie, the correct answer is room 0. This example highlights how delayed meetings are handled, how original start times affect priority, and why room selection always favors the lowest numbered available room. This is example 1. Got it? Yes, the explanation I just gave corresponds exactly to example 1 of meeting rooms 3. You can introduce it to viewers like this. This example demonstrates all the core rules of the problem in one place: room assignment by lowest index, meeting delays when no rooms are available, priority based on original start time, and tie-breaking when counting meetings per room. Because both rooms handle the same number of meetings, the final answer defaults to the smallest room number, which is room 0. If you want, the next natural flow for the video would be either transitioning into the intuition behind the heap-based solution or explaining why this greedy simulation is necessary instead of brute force. Now let's look at example 2 and understand why the answer is room 1. We are given 3 rooms, numbered 0, 1, and 2, and a list of meetings with unique start times. Remember the key rules. Meetings always prefer the lowest numbered available room, and if no room is free, the meeting is delayed until the earliest room becomes available, keeping the same duration. At time 1, all 3 rooms are free, so the first meeting is assigned to room 0. At time 2, rooms 1 and 2 are still free, so the second meeting goes to room 1. At time 3, only room 2 is available, so the third meeting is assigned to room 2. Now at time 4, all rooms are busy, so the fourth meeting cannot start immediately and must be delayed. At time 5, room 2 becomes free first. Since the delayed meeting started earlier than any other waiting meeting, it is immediately assigned to room 2 and runs from time 5 to time 10. At time 6, the fifth meeting arrives, but once again all rooms are occupied, so it is delayed. At time 10, both rooms 1 and 2 become free. The delayed meeting is assigned to the lowest numbered available room, which is room 1, and it runs from time 10 to time 12. Now let's count the meetings handled by each room. Room 0 handled 1 meeting. Room 1 handled 2 meetings. Room 2 handled 2 meetings. Since rooms 1 and 2 are tied, we return the room with the smaller index. That is why the final answer is room 1. This example clearly shows how delayed meetings, room availability, and tie-breaking rules all work together in this problem. In this problem, we are given multiple meeting rooms and a list of meetings, each with a start time and an end time. Our goal is to simulate how meetings are assigned to rooms based on strict rules and finally determine which room hosted the most meetings. The key challenge here is handling room availability, delays, and priority rules correctly. Step 1. Sort the meetings. First, we sort all meetings by their start time. This is important because meetings must be processed in chronological order. If meetings are delayed, the one with the earliest original start time gets priority. Sorting ensures we follow this rule naturally. Step 2. Track room state. We maintain 2 arrays. Room free at. This stores the time at which each room becomes available. Meeting count. This keeps track of how many meetings each room has handled. Initially, all rooms are free at time 0. All meeting counts are 0. Step 3. Process each meeting one by one. For every meeting, we extract its start time, its end time, and calculate its duration. Now we attempt to assign this meeting to a room. Step 4. Try to find an available room. We scan rooms from lowest index to highest. 2 things happen during this scan. We check if any room is free before or exactly at the meeting's start time. If yes, we immediately assign the meeting to the lowest indexed available room. At the same time, we also track which room becomes free the earliest. This is important if no room is available right now. Step 5. Assign or delay the meeting. There are 2 cases. Case 1. A room is available. The meeting starts immediately in that room. We update the room's free time to the meeting's end. We increment that room's meeting count. Case 2. No room is available. The meeting is delayed. We assign it to the room that frees up the earliest. The meeting keeps the same duration. We update the room's free time accordingly. We increment that room's meeting count. This ensures delayed meetings are handled fairly and correctly. Step 6. Repeat for all meetings. We repeat this process until every meeting has been scheduled. At this point, we have accurate room usage timelines and exact counts of how many meetings each room hosted. Step 7. Determine the final answer. Finally, we scan through the meeting counts. We find the room with the maximum number of meetings. If multiple rooms have the same maximum count, we return the room with the smallest index. This satisfies the problem's tie-breaking rule. To summarize, we simulate meeting allocation chronologically. We always prefer the lowest indexed available room. If no room is available, we delay meetings intelligently. We track usage accurately and return the most used room. This solution is clean, deterministic, and directly follows the problem's constraints. Alright, logic is in place. Rooms tracked, delays handled, rules followed. Let's run this against the test cases. Everything looks clean. Sorting done, room allocation simulated correctly. Now let's submit the solution and there it is, accepted. All test cases passed successfully. Meeting rooms scheduled perfectly. If this breakdown helped you understand the problem, hit like, subscribe, and share it with a fellow coder. More daily LeetCode explanations coming up. See you in the next problem.